What is gravity? I wish that I knew.
Einstein says it's actually a curvature in space-time caused by mass, but why mass causes a curvature in space-time isn't really known.
But physics has never been very good at explaining the origin of laws like this. It kind of glosses over that.
It's interesting because gravity is the weakest of the four fundamental forces, and yet on the large scale, it's the one that dominates.
I like these constants of nature that God put into this whole place to keep the whole thing faithful and working.
And most of us never have the insight to pull it all together and say, whoa, this is a big mosaic that's working for one grand purpose, our existence.
Our solar system is an amazing balance of celestial bodies in motion, as the planets and other objects orbit around the sun. It all works together like a finely tuned mechanism of a clock. The Creator designed things like magnetism and electrical forces to interact in amazing ways to hold things together. The force that has the greatest impact on motion of our solar system is gravity. And yet this mysterious force has left scientists asking even more questions.
One of the questions people ask, what is gravity?
What is gravity? I wish that I knew. I could win a Nobel Prize in physics for that one.
So gravity seems to be a very constant force. Again, even though we don't understand it, it's invisible, but we can measure it, that it's a very precise force.
Gravity essentially is the acceleration or the force between two objects having mass.
If you had two masses out in space, they would eventually pull together by their mutual gravity. Even human beings, you have your own personal gravitational field. It's just very, very tiny. You can't notice it, but the Earth being made up of many, many atoms is a much larger gravitational field. But we observe this thing, we call it gravity, but what is it?
Gravity is interesting to me because it's ubiquitous. I mean, it's all around us. It affects everything we do. We just take it for granted.
Gravity, we just live with it. It holds us on the ground. It makes the rain fall. It keeps the moon going around the Earth. We can write the formula for gravity. Isaac Newton did that back in the 1700s. We can do all the calculations with it.
The first good theory of that was Newton's law of gravity, which is every object in the universe attracts every other object with a force directly proportional to the masses and inversely proportional to the square of the distances between them. And one of the big questions that Newton had and others had is this action to distance concept. You've got the sun sitting here and the Earth sitting here, and through empty space of 93 million miles, somehow the Earth knows where the sun is, it knows how far away it is, the distance, and it knows its direction, and it knows its mass. And it knows its own mass, and it correspondingly responds with that acceleration it's supposed to have. That's really, really weird when you think about it. Just magically this happens through distance. Well, all that Newton's law of gravity is doing is describing what we see. It doesn't tell us what gravity is, just describes how it behaves.
Now there are different theories on just what gravity really is. Maybe there are small particles that connect objects. They're called gravitons, kind of streaming back and forth between the moon and the Earth like an invisible rubber band. We've never been able to measure a graviton. Another idea is that maybe gravity is a curvature of space.
Einstein said it's a curvature of space-time. Wow, it takes a little bit of explanation, but basically if you imagine two straight lines parallel to each other, if they're in a normal plane, they'll never intersect. But now imagine them on a curved surface, then they could curve together and intersect. Gravity is like that. You take two particles that are on the same trajectory and eventually they intersect. What we think of as a force, Einstein says is actually a curvature in space-time caused by mass. But why mass causes a curvature in space-time isn't really known.
If you could imagine something like a trampoline, put a bowling ball in the middle of it so there's a low spot, and then if you would roll a tennis ball onto the trampoline, how it might kind of, it'd be on a slope, so it'd be caught. It might go round and round a few times before it falls into the bowling ball in the center. Likewise, current idea is that gravity is a curvature of space, and the Earth makes a small depression, and so the moon is sort of on a slope, and round us it goes and can't get away. And a person says, wait a minute, I can understand a trampoline, but three-dimensional space, how can gravity be curved? It's all mathematical. And often math leads the way to reality. So there may be some truth to this contraction or expansion or curvature of space.
Space is something, it's not an empty thing. It's a fabric they sometimes talk about. It's like an XY coordinate system, except you've got 4 dimensions, of 3 of space and 1 of time. Imagine a piece of graph paper with 4 dimensions rather than just 2 dimensions. And the location or the mass making up the sun alters space, it bends it, we say it warps it, and we can write an equation that describes how the thing is warped mathematically. And when it warps that, bends that space-time, that causes the space around it to bend, and that bending transmits out to where the Earth is, and the Earth is moving forward in time on the space-time thing, and when that warping is there, it then follows a curved path in that space-time, and that curved path in our normal way of looking at the world appears as acceleration.
You may have heard all the hype about the Higgs boson. It's supposed to be the particle that gives mass to all these other particles, and then their mass causes space-time to curve, but why that is not known.
Our physics books are just descriptive, it describes them. But physics has never been very good at explaining the origin of laws like this. It kind of glosses over that, the origin of anything actually. So I think that they're more designed, showing how it all came to be.
So all Einstein was doing was he was offering a little deeper level as to how that information of the sun's location, mass, and position, distance, and so forth is transmitted to the Earth. So he answered that question a little better. But he didn't say why. It's again descriptive. So we're unsure at a deeper level now, as it turns out. But it's an interesting theory, but again, we don't know what it is. All we can do is describe what it is.
It's very constant. We can measure it to many decimal places, at least the gravitational constant. I like these constants of nature that God put into this whole place to keep the whole thing faithful and working.
We find that Kepler's laws are explained by Newton's laws of gravity and motion, and Newton's laws of gravity are explained by Einstein's discovery of the nature of space-time, and so on.
But that's still a description. It doesn't explain why it's that way, how it's there, and that goes back to the fundamentals of gravity and God's hand, I think. However He does it, keeping it going.
As scientists strive to better understand the forces of gravity, we can observe how objects interact with one another. When we do, we can start to grasp how this mysterious force works.
Mass is what sets the gravity, the gravitational field. You can think of mass as creating gravity. It's the only thing that creates gravity, only mass, that's it. But there are certain other effects. There's an effect called frame dragging. If you have an object spinning at very high speeds, it'll actually twist the fabric of space, and it'll cause objects nearby to rotate a little bit. It's a type of gravitational force, if you want to call it a force, but it's one that's very difficult to detect. There's an experiment, Gravity Probe B, that's designed to detect frame dragging around the Earth. I think it's met with some success. It's an interesting phenomenon, but the force of gravity is set by the mass of the object alone.
We see the effects of gravity all around us, but it's not only the force holding things together. The Creator has designed other forces that are at work all the time.
Some people confuse magnetism with gravity. They're two different forces. They're two completely different forces, actually. The electrons are negative, and you got protons with a positive charge. There's an electric field between them. You can have magnetic fields like a bar magnet. And those two are linked. Magnetic fields and electric fields, you can use one to create the other. Electric fields can be repulsive. If you take two particles of like charge, they repel. With gravity, if you take two objects with positive mass, they attract. So it's opposite in direction of the electromagnetic field, interestingly. There are two other forces too that a lot of people don't know about, and that's the nuclear strong force and the nuclear weak force. And these two forces, the reason we're not aware of them is they only take place at very short scales, things within an atom, for example. And we believe it's the strong force, for example, that holds all the particles together in an atom. Because if you think about it, you got a bunch of protons in there, they're all positively charged, they ought to repel each other. There's obviously a greater force that's holding them together and that's the nuclear strong force. It's the strongest of all of the forces, followed by the nuclear weak force, then the electromagnetic force, and then the distant fourth is gravity. It's something that all massive particles have. Anything that has energy has mass, everything therefore has its own gravitational field, and it's attractive only. It's interesting because gravity is the weakest of the four fundamental forces, and yet on the large scale, it's the one that dominates. Gravity is the one that keeps the galaxies together and keeps the solar system orbiting and so on. Why is that? Well, for one reason, the two strongest forces, the nuclear strong force and the nuclear weak force, have limited range. They peter out after a certain distance. By the time you get outside of an atom, well outside of an atom, those things are negligible. So on the largest scales, gravity is what determines the shape and things like galaxies and planets. The reason planets are round is because of gravity. Or the reason the sun's round and the reason planets' orbits are the way they are. That's all because of gravity. So on the largest scale, electromagnetic forces tend to be negligible, and the only one that's left is this meager gravitational force. And you add up a lot of atoms and it gets pretty strong after a while. And so you can even have things like black holes where gravitational force is extraordinary.
So while gravity is the weakest of the four fundamental forces, it exerts the most pull on objects throughout the universe. There are some places in which gravity becomes so powerful that not even light can escape.
Black holes are a fascinating phenomenon. I love them. I'm so glad God created them. They're a test of physics. And I think that's probably one reason why they exist, is God gave us so we could understand certain physics. They're all at a safe distance from us to where they're not really a problem. There's something that was predicted by Einstein's theory of general relativity, but even before him, people had considered the idea of dark stars. Somebody thought, you know, if the gravity of a star was strong enough, then when its light goes out, it should fall back. A dark star. Einstein confirmed that that's kind of what they are, really. The gravitational field around a black hole is so strong that even light can't escape. But we now understand the physics of it a little differently, because we now understand that gravity isn't a force like the other three. It's a curvature of space-time, at least if Einstein's right. And so the way to think about that is to think about like a lake, and you have boats going along this lake and the sailboats and whatever, and those are like particles, and the lake is like space. Okay, and you got certain boats that are stuck on their highest throttle. Those are like photons. They have to travel at a certain speed. Light always has to travel at the speed c, which for the sake of argument will allow it to be the same in all directions, which Einstein says we can do. Now what a black hole is like pulling the cork in the middle of that lake and the water starts to funnel down into that hole. And so what happens with all the particles? Well, it's not like they're experiencing external force. It's not like wind is pushing them in. What's pushing? Well, they're just going along with the ride. They're going along with the water. At a certain point, the speed of the water matches the speed of those speedboats. And so even if they're directed outward, the water would go underneath them like that. They're like salmon trying to swim a stream, but they can't quite make it at a certain point. And so the light would actually be stationary at a certain radius around a black hole because it's outward directed, but space is falling in underneath it, and light's moving against space. And that distance, that radius, that's the Schwarzschild radius. And we call that an event horizon. And that's the point of no return, because if nothing can move faster than light. If light can't escape, therefore nothing can escape. Once you get inside that radius, you're dead.
Well, there are black holes out there, and we have, almost every galaxy has one that has probably the mass of 1 million stars or more in it, and our galaxy appears to be no exception. So near the center of our galaxy, as you approach this region, you reach a point just outside the event horizon of that black hole. The gravity is going to be pretty strong. And it's strong enough to make the stars whirl around very fast, rapid orbits. So that's how we know how much mass is in it. And yet the whole region where all that mass is not at all bright, it's dark. And so we don't know anything else that would match that description other than a black hole.
We see stars that orbit around black holes. We know they're there. But how do you know what the inside of a black hole is like? Technically, only a Christian can, because we assume that the same laws of physics that apply here apply inside a black hole. Now, what right do we have to assume that? God has revealed it to us. God's told us that He's universal. He upholds the entire universe by the word of His power. And so we trust that the same laws of physics that work in a laboratory where we can experiment also work inside a black hole. But a secularist could never, ever know that.
When we think of the power demonstrated in black holes, it helps us to better appreciate the amazing power of God Himself. Black holes appear to have strong gravitational fields that absorb nearby matter. But could the opposite be true? Are there celestial bodies that repel matter?
White holes are essentially the mirror image of black holes. It was a term, white holes, and it was entertained for a while in the 1970s by relativity experts. A white hole would be stuff where the matter is expelled out of it. It wouldn't fall out. It would have enough energy to just expand out through the event horizon. As the matter left the white hole, the event horizon would shrink and shrink and shrink until eventually it's all gone, and then all you're left with is matter moving out away from the center of the former white hole. Now, relativists don't know of any natural way you could have a white hole. There's a minority school, George Ellis was one of them, I don't know if he still believes this, that thinks that white holes could emerge naturally, that a black hole would collapse and then matter would start coming out of it and it would be a white hole. That's a mysterious area that the theorists don't know much about.
Isaiah 55:9 says, "For as the heavens are higher than the earth, so are my ways higher than your ways, and my thoughts higher than your thoughts." As humans, we're simply doing our best to understand God's creation. So when it comes to things like theorizing about white holes or trying to understand gravity, we can ask big questions like, how do they affect our world?
What would the world look like if there's no gravity? If there's no gravity, you can't have planets, you can't have stars, you can't have anything. You could have chemical bonds holding things together. The major forces that shape our universe are gravity.
I can't even contemplate how different our world would be without gravity. Gravity seems to be the dominant force in the universe. Most of our cosmologies rely upon that. Some other people think that it's not, that plasma effects, electromagnetic effects, I think they're wrong. If gravity weren't the dominant force, we would not be orbiting the sun. We could not have a stable source of energy. The world would be dark and cold almost all the time. Life would be impossible. So gravity is one of those things that really literally and figuratively holds the world together for us.
And so the stars would not fulfill their purpose of being for signs, seasons, days, and years. You can't have stars at all because the outward force of the pressure from the light would be unbalanced. And so stars would just disperse into space. There'd be no getting around that. You can't have stars, you can't have the sun, you can't have orbits because orbits are all caused by gravity. Life as we know it really couldn't exist without gravity.
So God has graciously provided all that we need to live here on Earth. It's obvious that gravity is designed to keep our world in perfect balance, and that includes the largest gravitational body in our solar system.
Believe it or not, even from this distance from the sun's gravity affects us. For one, it causes the Earth to orbit the way that it does, which means there's a significant amount of gravity from the sun right here. Secondarily, it's partly responsible for tides. Now, the moon has a greater effect on the tides, not because it's bigger, but because it's closer. It's much closer than the sun. And so about 2/3 of the tides are caused by the moon, 1/3 by the sun. And that's why when the moon and sun are at right angles, you tend to have the weaker tides. Whereas with the moon and the sun are aligned, either in the same spot or opposite, the tides tend to be much stronger. So people that live near the coast know that sometimes you can have the weaker tides and sometimes the stronger tides, because the sun does contribute to the gravitational pull on Earth's oceans.
gravitational pull is critical to life here on Earth as we spin and orbit around the Sun. But what about the spin of the Earth? Is its centrifugal force stronger than the meager force of gravity?
One of the questions people ask, if we're on a rotating planet, why are we not flung out into space? Believe it or not, that was an argument that was used early on against the idea that the Earth could be rotating. People say, you can't have a rotating planet, people would be thrown out into space. People know about this so-called centrifugal force that throws you outward and so on.
Centrifugal force, in many respects, is a misnomer. It's invented to explain why things slide across a car seat when we go on a curve. It's actually just a manifestation of Newton's first law. An object at rest remains at rest or moving in straight line motion. You turn, it keeps moving straight, but it looks like it's turning. You do have what's called centripetal force or centripetal acceleration on a spinning object. There is a slinging effect. When you have a rotating body, it tends to sling outward. That's how centrifugal clutches and such work. The Earth does this. There's a bulge at the equator. It actually spreads out like this so that the diameter through the poles is actually a few miles less than the diameter through the equator. But since the Earth is 8,000 miles across, you don't notice. It's a very, very good, to approximations, a sphere. Jupiter rotates very quickly, and it's gaseous for the most part, or not solid. What happens there is it gets very oblate, and it's obviously oblate to a telescope many times. It's not round, it's like this, a little oval sitting there. That's common. Every object that spins is going to be an oblate spheroid. We see stars like that, the planets, the sun slightly is like that. It's nothing unusual. It's a nice balance. If it's rotating too quickly, then the stuff flattens out to the point that stuff flies off. And if it had the ability to do that, it would have done it a long time ago. So the fact is, it's self-regulating. It's very unstable to be spinning that rapidly.
Well, the fact is, the Earth's gravity is what keeps people pinned to the surface, even though it's rotating. The outward apparent force of this, what you might call centrifugal force, that outward apparent force, is very small, really, for an object like the Earth that takes complete 24 hours to rotate once. It's a weak force. It's there, but it's weak, and it's overwhelmed by the force of gravity, which is what keeps us all pinned to the surface of the planet.
Not only does gravity keep us secure here on Earth, but it keeps the planets in their proper orbits. But it may actually have a bigger effect on our world than we realize.
One of the interesting things that was discovered by Einstein is that gravity actually affects the passage of time. It's a remarkable thing, and it's something that's predicted by his theory of relativity, and something that has now been confirmed, gravitational time dilation.
You know, time is an interesting concept in physics. It has an arrow. It only seems to move in one direction as time goes by. A little bit like a rubber band. It can be contracted, it can be expanded.
We're actually able to see this effect. For example, clocks at sea level tick a little bit slower than clocks on mountaintops. We can measure that effect with atomic clocks. I won't go into too much of the details of why it happens, but it is a logical consequence of Einstein's understanding that space and time are affected in order to keep the speed of light constant. The round-trip speed of light is constant in a vacuum. And in order for that to be the case, space and time have to bend, and gravity as well. Gravity will affect the passage of time, and it affects lengths by a bit as well. What you consider to be the length of a particular object will depend to some extent on what gravitational frame that you're in. The time effect is the more significant one.
I did one experiment in graduate school where we were working with half-lives, how long radioactive materials last. We had a tower. We had the radioactive material at the bottom of the tower. We measured very carefully what its half-life was, and we took it up to the top of the tower, which was really further from the center of the Earth, and it was a different half-life. Now this is only a nanosecond type change, very small change, which we were able to measure, showing that there is we call it a gravity dilation of time. So gravity affects time, and motion affects time. But again, it's kind of comforting that we can't play games with time and change it by a grand scale. These are very microscopic changes. I've got to say, God controls time and the unwinding of the universe, and we can't go back in time and things like that.
So there are great mysteries when it comes to gravity. How does it work? How does it actually affect time? There's so much to learn. For example, have you ever thought about how this mysterious force attracts objects to one another?
In Newton's time, forces were thought to be instantaneous, that when, if you wiggle a mass over here, its gravity would instantaneously affect the object over there. We now know that's not the case. Gravitational field or an electric field or whatever, they actually propagate at the speed of light. There's a finite time, there's a time lag between this object and this object. Strangely, there is a very interesting phenomenon in quantum mechanics called quantum entanglement, where one particle seems to affect another one at tremendous distance instantaneously, faster than light. It's very strange. It's not something that I pretend to understand very well. I'm not sure anybody really understands it terribly well. But by measuring one particle over here, you do what's called collapse its wave function. You force it to be either spin up or spin down, for example, whereas it was an indeterminate state before that. When you do that with this particle, it will instantaneously affect another particle if those two were together at one point. So suppose you create a particle and antiparticle pair. One shoots out this way, one shoots out that way. If you affect this one, if you measure its spin state, it will instantaneously affect the other spin state. Amazing. But there's no way to use it to send information faster than light. Apparently the rule of the universe is that information cannot travel faster than light, and so there's no way to use it because you can't tell which is the cause and which is the effect. But it is faster than light, it's instantaneous effect. It's called quantum entanglement.
It's amazing how little we really understand about gravity and ultimately our universe. But God's Word gives us answers for those who reject the biblical account. You see, they have a challenge. Where did the universe come from in the first place? Well, gravity might give us clues to answer this question.
Gravity is actually useful in showing that the universe has a finite age.
Sir Isaac Newton, he believed in the eternal universe because it went back to the ancient Greeks. And so he thought that when he applied gravity to the universe, everything would be attracting everything else. And if the universe is eternal, it's always been that situation, you would have plenty of time to attract everything and collapse it into a heap at the center. You look around, the world doesn't look like that. So obviously you have a problem.
The reasons for that is we know that the galaxies are expanding, and if the universe were eternal and if the galaxies were all just sitting there, gravity would pull them together and they would collapse. So you can't have an eternal static universe. Now it turns out the universe isn't static anyway, it's expanding, but gravity would tend to slow that expansion a bit.
So you have two ways of getting out of that. One of them would be to reject the eternality, which is the obvious approach to me, it would seem. But he didn't. He was so steeped. You get in that rut, it's very hard to think outside the rut, outside the box, as it were.
Back in Newton's time, that was a problem. Newton knew about gravity. He didn't know about the expanding universe. And he wondered about this. He still had some residual thinking in terms of an eternal universe. Even though he did believe that God created it, he was still thinking eternal, static, unchanging. But he knew that couldn't be if there was gravity in it.
He instead hypothesized the universe is not only eternal but also infinite. And there, if you're a star sitting here, you've got stars over here pulling you this way, but you've also got the same number of stars over here. Infinite universe, there's no center, thinking Euclidean, leading not curved but just straight geometry. So you're being pulled equally in either direction, so you're not going to be pulled. Ditto over this direction, that direction, and that direction. So you end up with a stable, what you call a steady state universe. Interestingly enough, 80 and 95 years ago, when Albert Einstein did a similar thing with his theory of gravity, general relativity, that didn't work. All the matter would be pulled to the center, but when that happened, if you applied to an infinite universe, it still wouldn't work. You would basically have gravity pulling in like this. And so what he did is he threw in what's called the cosmological constant repulsion term to try to prevent that from happening, because he wanted the universe to be eternal. And again, making it infinite didn't solve the problem. That's one of the quirks or the differences between a Newtonian gravity and general relativity gravity. Right after that, George Lemaitre and Alexander Friedman and others realized that Einstein had missed something. There are two possible solutions. The universe is contracting or it's expanding, and this idea of it being stable against either one of those is kind of contrived. And that's what led into the belief in the expanding universe instead. So gravity, if left to itself, and that's the only thing affecting it, would tend to pull everything to the center. That's not the only thing acting. If that's the only force acting, major force acting, only major effect, and if it had eternity to do that, infinity to do that, it would have already done it. And that's obviously not the case, so therefore I think we can reject either gravity as being the sole thing involved or the eternality.
From a biblical worldview, we know that it was God who created the heavens and the earth not that long ago. The motions of all the planets follow the laws of physics that He set up from the beginning.
One of the interesting things about the law of gravity is in the formula for it you have F equals g/mm over r squared. One of the questions is why r squared? And is it r squared? Why exactly to the power of 2 as opposed to 2.1763? In a chance universe, why would that be?
Sir Isaac Newton was very keen on that aspect because he found that the force of gravity is inversely proportional to the square of the distance between the two bodies. You write 1 over r squared. And he reasoned that it was exactly 2, because if it's not exactly 2, you don't get stable orbits. The orbits actually change on you over time, and they don't. He very clearly saw that as a design inference.
In the creation worldview, we would expect that God would make some of the laws of physics understandable because He expects us to study and understand the universe. And so, of course, they obey nice, neat equations, and even the variables within them are nice and orderly and so on. There have been experiments to find out, is it exactly to the power of 2? And the answer is, within our ability to measure, it is. There have been certain experiments that have found that it's to the power of 2.00000 whatever. As far as we can know, it's exactly to the power of 2. And isn't that convenient? And I just wonder how my secular colleagues sleep at night thinking, you know, why is it exactly 2 when it could be anything? It's a chance universe after all.
Now today we're very clever. They say it's the result of a three-dimensional space that we have, and you can show in physics and high-powered physics that that's indeed the case. But then that begs the question, because, well, why do we live in 3 dimensions? Why not 4? Why not 6? Why not 2? You know, so it's true that 3 dimensions actually necessitates that. But on the other hand, why do we have 3 dimensions? They never occurred to ask that. So I'm with Sir Isaac on this one. The fact that it is inverse square. By the way, they've checked it in experiments. It's 2 to like 18 decimal places. There's a good reason to believe it is exactly 2, but it's good to test that sort of stuff. And so gravity is this marvelous thing that shows stability, and any other power of the distance would not allow that stability to be there.
Proverbs 25:2 says, "It is the glory of God to conceal a matter, but the glory of kings to search out a matter." Well, God is the one who created gravity. It's been the glory of scientists throughout the ages to unlock the mysteries of this force.
Isaac Newton was a brilliant scientist. Most people know that. Most people don't know that he was actually a Bible scholar as well. He had a tremendous amount of respect for God's Word. He was apparently a Christian. He had a nuanced view of the Trinity, but I do think he believed in the Trinity based on his writings. He was very interested in Scripture, and he believed Scripture, and he believed in creation. There's some debate about whether he held to a young universe, although I think he did. He confirmed Bishop Ussher's chronology, and so that suggests that he did believe in a creation thousands of years ago. It's interesting too, when you read Newton's works, you get the impression that he thought that he would be remembered for his writings on Scripture rather than his many scientific discoveries. But a brilliant mind, and he expected the universe to reveal its secrets because it was upheld by the mind of God, and because God had created our minds with the ability to understand the universe, and naturally mathematics being, as it were, the language of God, the universe would obey laws of mathematics. And he was able to make more discoveries than just about anyone since or before him. The number of discoveries he made are phenomenal. The discovery of calculus, the discovery of the nature of gravity, the laws of gravity and motion, optics. He made more discoveries than any person has a right to, really. I really admire him very much for that.
Great scientists in history knew that they were piecing together the mysteries of God's creation. As a matter of fact, Johann Kepler, the founder of physical astronomy, once said he was thinking God's thoughts after him. And it's also true when we study gravity.
scientists are portrayed as having the truth about something. Evolution is something that's not to be questioned. Cosmic origins and so on, they have it all figured out.
Turns out evolutionists would just hypothesize that gravity just happens, just is. It's just one of those things. Now, there are a lot of things about our universe that seem to be contrived for our existence. People have called this teleology or design of purpose. Other people call it the anthropic principle. That was coined, I think, in 1973 by Brandon Carter. A number of things about the universe that would suggest design for our purpose of being here. And people have responded to that in a very positive way. They say that the universe is just that. It appears to be design. All this design is just simply an illusion of design.
If you look at how gravity has been understood, the crowning achievement of this was Isaac Newton's equation, which purported to explain gravity and did so for several hundred years. And then along comes Albert Einstein, comes out with his theory of relativity, totally changes our understanding of how gravity works. In fact, gravity was one of the primary reasons in the early 20th century that caused a revolution in the philosophy of science, where people started to think of science less as seeking after truth and more in terms of a model that's believed today but that might be gone tomorrow. And their thinking was, if something as fundamental as gravity was apparently misunderstood for hundreds of years, even though we thought it was clear truth, what else can we know for sure if something that basic can be changed? So I think that's a lesson for all of us, especially in the creation evolution discussion. Just because everybody believes something today, even if we have an equation that predicts something very precisely, as I've heard it said, all scientific theories have a shelf life. If something so fundamental as gravity, after hundreds of years of successful predictions of an equation, if that can be changed, then how can we say that something much more nebulous, like our understanding about what happened billions of years ago, or even if there were billions of years ago, how can we say with confidence that that is truth?
One of the ways that gravity, and for that matter all laws of nature, show God's character is they show that He's a God who keeps His promises. Gravity is one of those things, like other laws of nature, that is consistent over time and space. And that's something that God has promised in His Word. In Genesis 8:22, He promises that the basic cycles of nature, signs, the seasons, the days and years and so on, and day and night cycle, those will continue in the future as they have in the past. And gravity, along with other laws of nature, demonstrate that. We expect gravity will be tomorrow as it was today. We expect it will continue to be that way in the future. It's one of the things that makes life possible on this planet. And so it shows God's character, His consistency, and the fact that He loves the creatures that He's made.
Absolutely, God designed gravity as He designed everything else. He took care of a lot of details. And we're looking at little pieces over here. We look at gravity a little bit, and we look over here at the Earth, and we look at the Moon, the Sun, these little pockets of different things. And most of us never have the insight to pull it all together and say, whoa, this is a big mosaic that's working for one grand purpose, our existence. To a creationist, you see that better. If you're an evolutionist, you're looking at little tiny pieces here and there and never looking at holistically in terms of one big package. Because if you do, suddenly your worldview is challenged because you start seeing design showing up and you want to deny that at all possibilities.
In Colossians 1:17, we learn that Christ is the one that upholds all things. We see this when it comes to the amazing force of gravity. It is the very glue that holds our solar system together and sustains life on Earth. It reveals the very character of God, that He is brilliant, powerful, and loving, causing us to worship and say that the heavens declare the glory of God.